In section 2.4 here, we want to consider numerical measures of variability or spread in the data. So let's look at an example here. We've got two data sets, 3, 4, 4, 5, that dot plot is graphed here, and 2, 3, 4, 4, 5, 6, that dot plot is graphed here. Notice that the mean x bar is equal to the median, the middle value is equal to 4 for that first data set. And that's because here we've got two values at 4, one that's 1 unit above, one that's 1 unit below, so it's going to average out to 4. And then the same thing over here for this data set. X bar, the mean, and the median are both equal to 4. So those data sets have the same center. But that's not all that describes a data set. We also have to consider variability. So one measure of variability is the range, which is just the biggest minus the smallest value in the set. So for this set here, our range would be 5 minus 3, which is 2. And then over here, our range will equal 6 minus 2, which is 4. So looking at the range, this data set is more spread out. It's got more variation around the mean. It's spread around the mean. And, range is very easy to calculate. However, it's just a rough measure because it only uses two values, the maximum and the minimum. So some notes here are that range is just a rough estimate. It's a crude measure. It only uses two values. So an advantage here, a plus, is that it's easy to compute. And a minus is that it's not very sensitive. It's that rough measure. So it only pays attention to the max and the min. We could have, all the other values could be, all over the place, or they could all coincide with 4, and we'd have the same range. So it's not very sensitive to what's happening with individual data. So we would like a better measure of variation, and that measure is what we call standard deviation. So first of all, we're going to define sample variance. So sample variance is the mean of the squared deviations using n-1 as the divisor. So here's a deviation. It's the individual data value minus the mean, and then you square it. That's a squared deviation. This sigma means sum, so that is summing up the squared deviations. And then you divide by how many numbers you have minus 1. And then that's logically equivalent to this formula, which is called a shortcut formula. It's a little bit easier to work with. Let's look at this formula. This is the average of the squared deviations is what you're doing. That's the variance. And then once you get that number, the standard deviation, you take the square root of the variance. It kind of undoes this squaring here. So now if you're talking about population instead of sample, you'll use sigma squared for variance and sigma for standard deviation. So let's look at that data set here, 3, 4, 4, 5. So that's the data right there. Here is the mean, 4. And then this is the deviation column, x minus x bar. So 3 minus 4, negative 1. 4 minus 4, 0. 4 minus 4, 0. And 5 minus 4, 1. And notice if you add up those deviations, you get 0. That always happens. That's why we square the deviations. Because if we just averaged the deviations, we'd always get 0. So we average the squares of the deviations. So negative 1 squared is 1. 0 squared is 0. 0 squared, 0. And 1 squared is 1. We sum those up, we get 2. So that 2, that's the numerator here. That's the sum of the x minus x bar squared column. and we divide that by n minus 1. N here is equal to 4 values. So we're going to take 2, so our s squared here is going to be 2 divided by 4 minus 1. So that's 2/3. That's your variance. So 0.6 repeating. And then the standard deviation is going to be the square root of 2/3. And if you enter that into the calculator, you will get approximately 0.82. Okay, so pause the video for just a second and try the same thing here for the second data set and see if you match me. So you should have had deviations of -2, -1, 0, 0, 1, 2. When you square them, 4, 1, 0, 0, 1, 4, add them up for a total of 10. So your s squared would be 10 divided by, there are 6 values here, so n is equal to 6. So we're dividing by 5. So s squared is 2. S is going to be the square root of 2, which is approximately 1.41. So bigger standard deviation here means more variation in the second set. So this is greater than the 0.82, which is telling us more variation. More variation in the second data set. Now you can also use this so-called shortcut formula to compute your standard deviation. So here you sum up the squares of the x's, and then you take the sum of the x's squared, divide by n, divide that whole thing by n minus 1. So the squares of the x's, so here's our data values, and they have a sum of, let's see, that's 7 and 9, 16. So that's the sum of the x's right here. And the sum of the squares, so let's see here, 3 squared plus 4 squared plus 4 squared plus 5 squared. So that's 9, 16, 16, and 25, which is 66. So that is 66 minus, and then this sum, that's 66, is the 16. So 16 squared, divide by n is 4, and then divide the whole thing by 4 minus 1. And if you compute this on the calculator, you get 2/3, that same 2/3. And then you take square root and you'll get the 0.82. And similar over here. Now you can do this with one variable stats on the calculator. Let's take a look at that. So we want to go to Stat and Edit, and then we will clear the data out that's in there, highlight the L1, clear Enter, and then I'm going to enter 3, 4, 4, and 5. Then we want to come to Stat and arrow to the right, Calc, and one variable stats is what we want, Enter, come down to Calculate, Enter. So there's our x bar of 4. Here's our standard deviation, 0.816, that's 0.82. That's the sample standard deviation, population standard deviation, 707. And that's where you'll find standard deviation on the calculator. So unless I ask you to do it by hand, just use one variable stats.